So first thing you should do, we see this question, what content are we being asked about? I'm going to argue no. So that's what the question is asking. What's the content area? So what do you think the competency is that would tie back to this? Is this asking about the branches of chemistry? No. It's not asking about forces. So we could lean into oxidation states. There's a little bit of dual overlap there. You could probably pull in oxidation states. This is actually nomenclature. Because if you're going to go through and put together to come up with a name for this compound, you would need to specify the Roman numerals because cobalt is not a metal you're responsible for knowing the charge on, which means you would have to specify it within the name. So this is technically a nomenclature question. Okay. How do we determine that charge? So officially what we would say is that we have 3 cobalts times an unknown charge, officially oxidation state, plus 2 nitrogens times their charge, and then this has to equal the overall charge. The overall charge being specified in the upper right-hand corner. So since nothing is written there, we know that's a 0. And if we're looking at this system, we're now being asked for X. We want to know the oxidation state on the charge on our cobalt. How do we figure it out? Requires one bit of knowledge that you have to have on this. We have to know the charge on nitrogen. So this is going to our common ionic charges. There are certain elements that we're supposed to know the charges for, particularly when we're looking at ionic compounds. How do we know we're looking at an ionic compound here? Metal and non-metal is the best option. It also says ionic, which is a pretty big tip-off. We're looking at an ionic compound. Because it's ionic, that means we can pull at the charge, the common ionic charge for our nitrogen being -3. That then has to equal our overall charge of 0, so we're getting 3x. If we push this the rest of the way through, we get 3x equals +6, x equals +2. Which means the ionic charge for our cobalt in this particular compound comes in as a +2. Does that make sense? Okay. So trying to find that area of content becomes relevant. If this is going to sit into that nomenclature question, we're not being asked specifically for a name or coming up with a formula. We're being asked to interpret the formula, and that is one of the pieces that we're supposed to do with nomenclature. Kind of make sense? Questions about it? Okay. Who asked? Is that you? Are you good with it? And calling it oxidation state isn't a bad idea. Arguably, you're more correct to call it oxidation state than you are calling that charge. So if we're being asked for this question, do we need a calculator? No. And that doesn't mean, oh, I can do my long addition. No, we don't need that either. Look at your answer choices. What do you see about your answer choices? Hopefully what you notice is that the numbers themselves are all the same. The only thing that's different between them is the number of sig figs. So this starts to hit kind of weird gray area. If you were paying real close attention to what I had done initially with this question, is I deleted some words that were associated with it. Those words are things that should be implied within the context of this. So anytime you're looking at a calculation, you should immediately be thinking, do I need to round this off? That's part of it. And that round off has to do with sig figs. So how do we do the round off here? And this is probably a bad question if I'm going to be honest. No, it's actually okay. So how do we do the round off?
I added first and then rounded to 3 sig figs because you choose the lesser sig figs versus
Cool.
more, right?
So you add up and you probably got 19436, be my guess. And then you said because I have 7.77 has 3 sig figs. And I have this with, was that 5 sig figs? You went through and said, I want to underline my 3 sig figs, so my answer should be 19.4 officially grams. Yeah? Does everybody agree? Whoa, so I got some yeses and some nos. Good. Okay. This is actually a no. Okay. This is more than likely what you're going to get tested on. Okay, because the rule that you're using is one you use lots. In fact, the vast majority of calculations you run use the exact rule that you try to manipulate, which is the number of sig figs. The number of sig figs that shows up in your calculation is only used for multiplication and division. Because this is addition, you get a different rule set. That rule set, I think, becomes a little bit easier to see visually if we write out kind of the longhand. Our answer is as precise as our least precise place, I think is how it goes. So if we go through and look at those numbers, that first number is precise to the thousandths place. The second number is precise to the hundredths place. Which means when I go through and I do the addition, yes, I'm still going to get that 19.436. My least precise place is that hundreds place. So I have to report to that place. Because the first insignificant digit is larger than 5, I will add 1. So my answer becomes 19.44 grams. Which does introduce an interesting kind of dilemma. We have more sig figs in our answer than we started with. That is an artifact of addition. When we do addition calculations, you very commonly will see an increase in the number of sig figs. It's very, very, very common. Okay. Conversely, if we subtract, guess what happens? Decrease in number of sig figs. Okay. And this is why when we do certain calculations, we try to set up the experiments to minimize the loss of sig figs. So if you remember using the burettes, okay, when you look at using a burette, your initial and final is how the difference between those is how you get an actual reading of how much liquid you delivered. Almost universally, you want a volume delivered that is larger than 10 milliliters. Because if it is less than 10 milliliters, you lose a bunch of significant digits from your calculation. Okay? You as students probably didn't even realize that that was something that was going on because that was designed in or baked into the experiment, and that's hard to see as a student. Right? Typically, the only place you would see it is when you ran an experiment and it gave horrible results. Then you start to pay attention to why you want larger differences.
If this was multiplication or division, what would be the rule for sig figs?
If it's multiplication or division, it's the fewest number of sig figs. So addition, subtraction has to do with the precision of your measurement. Okay. Multiplication and division is now just the number of sig figs. Okay. Any mathematical operation you do has its own rules for sig figs. Okay. Because the only operations that you really have to worry about are multiplication, division, and addition, subtraction. We don't have to drill into any of the other significant figure rules. Right? Officially in second semester general chemistry, they talk about logarithms. Right? Logarithms have their own set of sig fig rules that I genuinely don't have memorized. Few people do, actually. Okay, so make sure you watch out for that. It is a common issue. Be aware. What next?
Could you do 49?
Okay, never mind. So I've complained about this kind of formatting of a question before in the past. Still something that kind of holds true. If we're going through and looking at these two things, what is the unit on the percent that we're trying to look at? Should it be meters? Should it be liters? Should it be grams? Okay. Deciding what that unit is should be clearly stated. Okay. It should say the percentage by mass. Okay. Or you could see by volume. Why would we switch units? Yeah, it's going to come down to what phase. So if you're old enough, you may have heard of ABV, alcohol by volume. Why? Because the alcohol in that beverage is a liquid. So they're reporting it based off of the volume of the liquid because it's easier to measure the liquid volume than it is to measure the mass of that substance. When we're going through into this one, we're now looking at the inert gas compound. Gases are going to be a whole nother question. If we're looking at gases, typically we're going to look at trying to measure those either as pressure or by volume. But if we're going to do that, we would need a lot more information within this question. Okay? We would need to know the volume of the original substance. We would need to know the volume of each of those individual elements. And that's not an easy thing for us to just look up. Okay? Is the mass any better, though? Yeah? Why is the mass better? Because what does the periodic table give us? It gives us the atomic mass or the molar mass. I would prefer you to have it memorized as molar mass, but atomic mass works equally well in this particular scenario. So what we could go through and do is say, well, if I want the percent by mass, I'm talking about the mass of platinum, okay, PT divided by the mass of the total sample, the mass of the xenon platinum hexafluoride. Okay, so what is the mass of platinum?
I can't read this.
195.08 officially grams per mole. Okay, because we're looking at this as consistent counting units. We don't have to stress about the mole, and we could really just drop it in as grams. Okay, what's the mass of xenon? Where'd it go? There it is. 131.29 plus the mass of our platinum, 195.08, plus the mass of fluorine, 19, but I've got 6 of them, so I could then just multiply by 6. Now it's just a question of entering it into the calculator. These were all in units of grams, so what's going to end up happening is the gram unit is effectively just going to cancel out. Looks a little bit weird canceling like that, but it's just going to cancel out, and you'll get your final answer, which was, did anybody do it? No? Let's see if I can spitball it. 6 times 20, 5, so that's 120, 130, 250, 450. We're saying 200 divided by 450 as a ballpark. Slightly less than? Yeah, slightly less than 50%. Does that give me an answer? Ooh, I would say that. What'd you get?
Bottom one is 440.37.
It's around like 44.2%. What's the good?
Hate math. Sometimes estimation works for you. Okay, so all this stuff I did down here was just me estimating. This is Mike playing. When you go through and actually run that calculation, the 195.08 divided by your 440 came in at 44.3%. Make sense? Whose question? You good with it?
So just basically look out for this, what phase it's in, and then, or just see.
Two ways to answer that question. Okay, so the first way, the most appropriate way. When trying to calculate or determine your percentage, what you should be doing is, yes, paying attention to the phase. Because the units of that will change your percentage depending on what you're looking at. Okay? Whoever puts together the finals does not seem to acknowledge that volume is a unit when it comes to percentages. So if you're being asked for percentages, they're giving it to you as mass. Okay? And it's probably an artifact of what we just talked about. If we're going to ask by volume, what else do we have to give you? We are going to have to give you all the volumes. For masses, we don't have to give you anything because the periodic table already has it. Okay? So it's less a dig at them or whoever put it together. It's more a dig at, it's just easier because we've already given you masses. So if you're being asked for percentages, it's mass. Good old classic stoichiometry question. Okay, we've got a lot of kind of pieces put together. We're being asked for the moles of pentane. I would probably get lazy and just write pent. I probably actually would not write out C5H12 because pent is easier for me to write. Must react to yield 2.4 moles of water. So depending on kind of my mood and how much I've gone through and memorized by doing a whole bunch of these processes, I may not actually bring in that 2.4 moles of water right away. If you've been doing this in the past and you're happy saying that's the only thing I'm given, so I can put 2.40 moles H2O and put that in the numerator, that's fine. Okay. You're probably going to be following in that process anyway. Okay. What might be a good reason for placing it in the numerator? Yeah. Okay. We're solving for moles of pentane. I have moles of water. It's at least the same measurement unit. The substance is different. So that's reasonable. I could start with that as a good starting point. Once I've got that starting point, I could go through and then acknowledge, well, I don't want moles of water, but I do want moles of the pentane. What's changing in that conversion factor? This is a substance conversion, and a substance conversion is not found in molar mass. Molar mass is the moles to grams ratio. Here we're looking at changing a substance. This is from the balanced chemical equation. So I go back to my chemical equation. Look at that. Handily, I was given a chemical equation. Okay, is it balanced? Okay, I would know that by looking at the coefficients in front. Since there's conveniently this blank line sitting in front, that's a pretty big tip-off that they probably did not bother to balance it for me, which means to go through and answer this question, I've got my work set up, but now I actually have to balance to begin with. So carbons on the left, 5 carbons on the right, 1. So that doesn't balance. To make that 1 into a 5, I need a 5 there. What element should I balance next? Why should I balance hydrogen first, then oxygen? Oxygen shows up in lots of different places. So if I needed to balance that oxygen out, particularly on the right-hand side, what number do I change? Do I change the 5 or do I change that box number in front of the water? Because oxygen shows up in multiple places, it becomes much trickier to go through and balance. So you should start with hydrogen that shows up in one place on both sides of the equation. Hydrogen on the left, I have 12. On the right, I have 2. Which isn't balanced. How do I make a 12 into a 2? need to put a 6 there so that multiplies through.
16 oxygen.
I can now go through and look at my oxygens. Oxygens on the left, I've got 2. On the right, I've got 10 plus 6, which gets me 16. How do I make the 2 into a 16?
Change oxygen on that side.
I need an 8. Okay. Now that I've gone through and changed a whole bunch of numbers, what should I theoretically do?
Write it out.
Should go back and check the work and verify that everything aligned. Okay, should we go back and check the work, or are we trusting it? Trust it? Okay, cool. If we're going to trust it, we can now go through and take those coefficients from our balanced chemical equation and draw them into our conversion factor. The number that shows up in front of our pent, of course it would bite me. Okay, our pent was a C5H12. The number that shows up in front of it is a 1. The number that shows up in front of the water was a 6. What happens? The moles of water cancel, and I would be left with the moles of pent. Is that what I wanted? Yep. So now I can do the math. 2.4 divided by 6, and I have my answer. Which is what? A third? 0.4? Yeah. Can't win them all. And you get 0.4 moles. Make sense? Why did they not write 0.4? They wrote 0.400. Sig figs. Is this a sig fig question?
Always a sig figs question.
It's not a sig fig question. Why not? All of them have the same number of sig figs. So we don't have to worry about sig figs. Okay? Typically, if you're being asked about sig figs, all of your answer choices are the same number. They're just different roundings. Okay? At least in a multiple choice. Make sense? Is that you, Ashley? Good? Questions about what's up there? Okay. What's next? 52 takes this question a little bit further, or that past question a little bit further with a new equation and new problem. So within that, I'm going to recommend you go ahead and start out your work for this. Once you've got some work established or moving through, then we can talk about answers. But we'll talk through some pieces behind it, just in looking at what people went through and did. So what I saw written down was a couple of things. Number one, people writing the question. You shouldn't be writing the question. You already know what the question is. It's already in the thing. You can just say question 52 and then start setting up your solve. Next part that I saw is immediately people going through and balancing the chemical equation. It is a chemistry class. I appreciate that you're going through and saying, I need to balance the chemical equation, because that's what chemistry is about. Though, do you need a balanced chemical equation to go through and solve? Okay, yeah? Based off of what? What evidence are you using that you need a balanced chemical equation? Yeah, you can get a conversion factor, but do I need that conversion factor? Okay, so I'm not trying to throw shade, I'm just trying to throw a thought process behind this. I would argue what you should be going through and doing first would be identifying what you want. I want the mass, so that'll be grams of aluminum. Okay, and I'm given as a piece of information 1.00 grams of hydrogen. So and actually they set up the units the same way here. Okay, I could go through and use that 1.00 grams of hydrogen and place that in the numerator, because the grams, the measurement unit, comes out the same. So that's great. I could put those together. Those as an equality aren't going to work. I'm going to need to do a substance conversion. Where do I find a substance conversion? In the balanced chemical equation. Okay? Now that I know I need it, I will try to find it. Okay? But if I don't need it, why should I bother to go and look for it? Okay? Should I look for the density of the substance? I don't know. Is it necessary to solve the question? No? Well, then I'm not going to bother. Okay? If it is something that's necessary, now I'll know to go out and look for it. The point of setting up your work is to highlight kind of those points that are necessary for you to go through and solve the question. Does that kind of make sense? And so if you're reflexing into doing something, you're likely reflexing into doing it for good reasons. You've done a bunch of practice, okay? But I would like you to pick up out of this class that you shouldn't just reflex into doing things because you've done it the same in the past. Okay? Does that kind of make sense? When going through and balancing that equation, let's go through and just real quickly nail that down. And by real quickly, how about you just tell me the answers?
2 aluminum, 6 HCl, 2 aluminum, Cl3, 3 H2.
Okay. So we've now got those coefficients, and now you could potentially try and go through and manipulate those. To that end, I will leave you to continue to work on it. Let's talk through a couple approaches. The way I've told you to be doing this is that now that we have this expression, we need to go through and recognize what we have and what we don't have, okay, or what we want to get rid of. So grams of hydrogen is not something I want in my answer, so I would want to place that in the denominator so those units would cancel. Ideally, I would place grams of aluminum in the numerator because that's what I want for an answer. Okay, but this is now asking for a conversion factor between the mass of one substance and the mass of another substance. That conversion factor does not exist. Okay? So what we've got to do is come up with something else. Deciding what that something else is comes down to you and where you want to lean into it. Okay? For me personally, you spent the frickin' time to balance a chemical equation. How about you use the chemical equation? Okay? And if we're going to use the numbers from our chemical equation, we have to recognize the unit. Yes, the substance, but what's the measurement unit from the chemical equation? Moles, which means I'm not looking at grams down here, I'm looking at moles. Okay? So I'm actually kind of shocked how few people did this conversion factor right away. Literally almost everybody went right into the balanced chemical equation, but then didn't bother to use it. Okay? So if you're going to do an action, make it useful. Okay? And if we go through and manipulate that, we've got 2 moles of aluminum. Where do we go? 3 moles of hydrogen. Okay? And perhaps one of the reasons why maybe you wrote this and then erased it is you go, well, what units canceled? No units canceled. Okay? So you've potentially made it more complicated because you don't have any units canceling. That's up to you. That's fine. Okay? You can always cancel those units later on. So we would move into the next step, and what do we know has to happen? I don't want the moles of H2. That needs to cancel. And what were you going to say? Or are you saying the same one? Okay, what else do I need to have happen? Because I don't know the moles of H2. I need the grams of H2 to cancel. Is that a conversion factor that exists? Yeah. That first one that we had came from our balanced chemical equation. And for this next one, we're looking at the relationship between grams and moles. That comes from the periodic table. So we go to the periodic table. Hydrogen has a 1 gram per mole, but I have 2 hydrogens in the formula of H2, which means I'm looking at 2.02 grams is 1 mole of hydrogen. What happens? Well, the grams of hydrogen cancel. That's great. And the moles of hydrogen cancel. That's also great. I didn't want any of those units, and fantastic. Right? I started with a conversion factor that got rid of nothing, and then I added a conversion factor that got rid of almost everything. And now when I go through and look at my units, what do I notice? I need the moles of aluminum to cancel, and I still need the grams of aluminum. This is, again, a relationship between grams and moles. This comes from our periodic table because the substance has changed. The number is going to change. Grams is 26.98 grams of aluminum is 1 mole of aluminum. What happens with my units? The moles of aluminum cancel, and what am I left with? Grams of aluminum. That's what I wanted. Now I can punch it into a calculator and get a number. Make sense? Okay. What we're trying to navigate all the way through is what's the next step? What's the thing that I see? Right? And one of the big challenges, I think, within this is that we all see something differently. Okay? And depending on who you talk to, you get different approaches. So for instance, I should have asked first, is it okay if I erase everything? That's good, because I did already. Okay? One of the approaches that, for instance, the tutoring center likes to leverage is to go, oh, I'm in grams of hydrogen. I can't do anything with grams. The most powerful chemistry unit is moles. So the first thing I want to do is convert that grams of hydrogen into moles of hydrogen. Where do I find that conversion? That's on the periodic table, 2.02, 1 mole. Okay? What happens? The grams of hydrogen cancel. That's great. I now have moles of hydrogen. Moles of hydrogen is not the same thing as grams of aluminum. Okay? I've changed the substance. So what do? I'm going to fix changing the substance. Where does that come from? That's my balanced chemical equation. The moles of aluminum was 2. The moles of hydrogen was 3. This gets rid of the moles of hydrogen. And now I can go through and say, well, I don't want moles of aluminum. I want grams of aluminum. That comes from the periodic table. And I get 26.98 grams is 1 mole. The thought process that navigates this is different than what we just talked about. All the calculations are still going to come out the same. Okay? But you're shifting focus on what thing you're trying to navigate through. It doesn't matter which path you take as long as all of the steps come into alignment. Okay? Kind of makes sense? Okay. I want to zero in real quickly on stuff coming off the periodic table. I will frequently see people interpreting that off the periodic table as 2.02 grams of hydrogen. And actually, they won't even do that. Typically, it's grams / moles, and maybe you will see hydrogen in there. Usually, that's left off also. That / is because of a frickin' typewriter. Are you using a typewriter? No. So stop looking at that and interpreting it as a typewriter. Okay? It is challenging to manipulate. I fully acknowledge and understand that. Okay? But you have to get away from that / system. That / system will show up on the final. Okay? Because maybe we decide we don't want to make you look at the periodic table. We'll give you the number with the unit, but it's going to get written in this format. What you should immediately be doing is converting that into the proper format. That / is setting you up with the fraction. That fraction is powerful because now you can potentially manipulate it back into the system you want to use. And for those people you've got the 2 in the numerator versus the denominator, because the units are changing. Where I place the units is important to my calculation. The number just follows the unit. So when I go through and insert that information that I pull off the periodic table, I wanted grams in the denominator, so the 2 is going to go into the denominator also. Make sense? Right. The point is tracking, number 1, your unit work, because that's what allows you to figure out the questions to go through and solve. Okay. The next part is knowing where that information is found. And if you're going through and solving these and you're like, I don't know where that information is found, you need to take note that this conversion, I don't know where this is. Get some help to find out where that conversion is found, if it even exists, and then make sure you start memorizing that when you see those units, you know where to look for those numbers. Because these numbers aren't coming out of thin air. We're pulling them from a source that you have access to. You just have to be aware how to use them. Make sense? Did anybody actually solve it all the way through? Actually, I know a couple people did. Was it 8.91?
It's 0.89.
You did something wrong with how you entered a number in. It's 8.91. Okay. Next thing I can kind of push as well, and I just remembered that. Next thing I can kind of push is, what calculator are you using? When you're going through and doing the practice exam and doing anything that involves a calculation, are you using the calculator that you plan on using on the exam? If you are not, you are doing yourself a disservice, because you're now learning how to use a device that you aren't going to have in a high-stress environment. Use the same device that you're going to use on the test, whatever that device is. Okay? I will say, if you're going to use Desmos is okay to use on the test. It must be test mode. I will be checking. And if I go through and I see that your phone isn't in test mode, okay, I will take your phone away and you will have no calculator. So make sure you get it in test mode to ensure that you're set up appropriately. And if you don't know how to do that with Desmos, talk to me and I can help you get through that. Okay? It's just an app. Okay? The next thing, if we go back to all of our past exams, 1, 2, and 3, you all had a cover sheet, and on that cover sheet had a whole bunch of information. Okay? Bunch of conversion factors, if you were actually reading it, directions that told you which common multiple choice to answer, which was actually true. Okay? 30% more or less. So if you just guessed that, you got 30% of the multiple choice correct. Okay? Sometimes a little bit higher. Okay? And where to write your name on the test. Okay? All of those things were points that you could have gotten if you read those directions. Those directions do not exist anymore. All you're going to get for the test is a periodic table, right? The activity series, probably the worst version of the activity series ever, but that wasn't my choice. And I believe the solubility rules. Okay? And again, the worst possible version of the solubility rules. Okay? Those are the things given to you. So you're not given any of the conversion factors that you're given on your regular semester exams. Okay? So look at those and decide which ones are important, which ones are not. You okay? Yeah, just check. Does that make sense? Okay. For instance, Avogadro's number was technically given to you on the exam. Okay. You need to have that memorized. I told you to memorize it. Okay. Milli, kilo, centi, you need to have memorized. Okay. You are expected to know those. Okay. That shouldn't come as a surprise because you should have already been using those. Could we still ask other things like inches to centimeters, right? Yeah, inches to centimeters. Yeah, we can. Do we expect you to have that memorized? No, we don't. Okay? But if we don't give it to you on the front of the exam, how could we possibly ask a question about it? It's in the question. Okay? So if you need that conversion information, it's in the question, not on the front of the exam. I would argue that's vastly easier, okay? Because if they're giving it to you in the question, it probably means you need to use it. Which again, I think is dumb, but make sense? So don't be surprised when that rolls around. Other questions? This one relies on common knowledge, which I think is sometimes a sketchy thing to rely on for a test, but that's what we're doing. What is the relationship between days and years? Okay, and before we start getting excited about looking at answer choices, what's our relationship? 1 year equals 365 days. Right? That's something that you theoretically should already know. Right? So once you've written that down, and again, I would argue you should write it down, you could then quickly look at your answer choices and be like, I don't see any equals in it. Because what did we do? Converted it into a fraction. Okay? So let's convert it into a fraction. Let's divide both sides by 1 year. What is 1 year divided by 1 year? 1. So 1 equals 365 days per 1 year. When we think back to our conversion factors, they all equal 1, which is why we can just put random numbers into our conversions, because everything they are is 1. Okay? So that's a valid expression. I could have just as easily done the opposite, and I could get 1 year over 365 days. Still equals 1. So far, so good? Again, we can go back and look at our answer choices and be like, stupid typewriters. Okay? How do I convert that into a typewriter system? 1 year / 365 days. The other one, 365 days / 1 year. So those are my two possible formats that I could see for a conversion factor. I can now go back through and try and manipulate. I would go through real slowly behind this. I'm looking for the 365 next to days and 1 next to year. 1 next to year looks good, 1 next to days does not, so that one's wrong. 365 next to both doesn't make any sense. 1 next to years, 365 next to days. That looks pretty good. 1 day, nope, that's wrong. 365 years, nope, that's wrong. My answer is going to come in cleanly as just this one. Kind of makes sense? Okay. There are potentially other permutations you could do of that, but I would be surprised if we saw any of those. In fact, I fairly confidently can say we won't. Does it work? Questions about that? This does introduce this stupid slash thing again. Right? Which formally I think we should get rid of and abolish, but again, you look at the entire context of how it's used. Typewriters, not typewriters necessarily anymore, but computers are used extensively, and when we type up a conversion, we almost universally will use that slash. So you have to be able to interpret it. It makes sense to be tested on it, even if it's a dumb, archaic system. According to the metric system, 1 liter equals 1 times 10 to the second what? Okay, so what we're now trying to do is drop in a unit into this space. Note that all of our choices are what kind of units? They're all liters, yeah. How I would argue them is they are all complex units. And if we think through what I've told you to memorize when we talk about our unit system, where does the power of 10 always go? With the base unit or the core unit, and that core unit is liters. Okay? So like, oh, well, you aren't allowed to do this. Remember, we are allowed to do this. You're just swapping where you want to place that number depending on the individual calculation. What do we mean by that? Okay, well, this milli is probably the best example of it. Okay? What is the conversion between milliliters and liters? 10 to the negative third core unit, liters, is 1 milliliter. Except, Giovanna, you just said 1,000 what?
Liters or milliliters
And
to what?
that is the exact issue I've got with it. 1,000 milliliters is equal to 1 liter. So who's right? They're both right depending on the context that you're trying to look at. Okay? This system here is effectively an artifact of nobody likes powers of 10 and nobody likes negative powers of 10. So what they went through and did is they took the original expression, and they said, I'm going to divide both sides by 10 to the negative 3. What is 10 to the negative 3 divided by 10 to the negative 3? 1 liter equals 1 over 10 to the negative 3 milliliters. You'd be like, well, that didn't make anything better. Okay? I had powers of 10 and negative powers of 10, and now I also have a fraction. This is horrible. Okay? Except through some mathematical manipulations, that negative just means run the calculation in the opposite location. Since it's currently in the denominator, I can flip it into the numerator, and I can get 10 to the 3 milliliters is equal to 1 liter. And you're like, well, I don't like powers of 10. Well, that's just a question of shifting the decimal place 1, 2, 3 places, and I get 1,000 milliliters is equal to 1 liter. That's where it comes from. And so people, again, manipulating things and trying to run calculations, it was hard to do powers of 10 and negative powers of 10, right, in your head. So what did they do? They did the manipulation once so they could memorize a new thing. 1,000 milliliters is 1 liter. Now you're just scaling things by 3 places, and that becomes an easier thing to do in your head, which is why people are told to memorize that. The problem that I have with it is that not only do you have to memorize your power of 10, but you also have to memorize the location. Because if I go through and take a look at kiloliters, 1 kiloliter is equal to 10 to the 3rd liters. And if I go through and look at it in the new notation, it's 1 kiloliter equals 1,000 liters. The placement of your number changes. I have a problem with that. That's very confusing. I have to memorize more information. And if you haven't noticed, I'm incredibly lazy and I don't want to memorize more information. So what I want to do is stick with the easiest conversion process so that I don't have to think about it and I just have to write down those numbers. I know where that number is always going to show up. It's not going to shift on me, and it helps to simplify my calculation process. Hi. If you're a nurse, do you think you're going to be dealing with kiloliters? Okay. So you don't have to worry about multiple different powers of 10 for your individual conversions. You only have to worry about one. And I could be wrong on that. You're probably looking at milliliters and that's it. Though kilograms, right? That's going to show up. Okay. But you probably don't have to worry about hectograms or nanograms or femtoseconds. Okay, so you don't have to worry about any of those extra units because you're only dealing with 2 prefixes. You can memorize those and be consistent in just memorizing those. So you shorten your workload because you don't need to think in a broader sense. When we talk through what's happening within an individual class, we're trying to provide you the broader sense. When you get to your field, you can narrow it. Kind of make sense? Which then sets us up to answer the rest of the question. Okay? We have to realize right away that this power of 10 thing is going to be a problem. We have to deal with where we're placing the number. The milli and the kilo were both 10s to 3s, plus or minus 3. Okay? So those should be off because we're looking at a power of 2. So those are out of the picture. What was deci? It's 10 to the negative 1. Centi? 10 to the negative 2. Oh, well, none of these answers work. Okay? Again, before we get too excited about saying none of these answers work, we have to apply this logic system all the way out. 1 centiliter equals 10 to the negative 2nd liters. Right? This thing I'm trying to match, I need a 1 in front of the liters. How do I get a 1 in front of the liters? Divide both sides by 10 to the negative 2. I'll get 1 in front of liters, and then I'll get this gross 1 over 10 to the negative 2nd centiliters. Okay, well, 1 over 10 to the negative 2nd is definitely not 1 times 10 to the 2nd. Do you have a calculator? And what happens when you use that calculator? 100 centiliters is equal to 1 liter. What is 10 to the second? 100. Yep, comes into perfect alignment, which means centiliters are our answer. Kind of makes sense? Please say I recorded that. Good. Okay. What we just walked through with those powers of 10 is the example that I was like, you won't have to worry about that when we looked at the day year one. Let's see if I can not screw this up. 1 year over 365 days. With a calculator, can someone tell me what 1 divided by 365 is?
0.0027.
Is that a valid conversion? It is. I'm changing the location of where I want my number. I want the number in front of years, which means I have to do the mathematics for it. What we just did with the years days is the exact same thing that's happening with our centiliters prefix. Okay? You typically don't see this manipulation with the years days because you're dealing with 365. You're dealing with a number that is not quote unquote easy to manipulate powers of 10 with. Kind of makes sense? Okay. Questions? So first and foremost, we've got a giant mess happening within the individual answer choices. So let's try and fix that first. This is A 5530 zinc. It's 30, whoops, not a slash. As I do this, is this more clear? Do you see what I'm doing now? And since I'm not looking up, I actually need a verbal confirmation of that. Thank you. That's the same thing. Oh, it's 30. So the first place I'll ask is, does that clarify it? Now you're like, oh, it's easy now. Okay, I fully expected that. Okay, so what we're talking about is atomic notation. Remember when we talked through this, or don't remember? Okay, but when we talked about it in class, we referenced this as not atomic notation, but as nuclear notation. So the point of this was trying to model what's happening within the nucleus. Okay, so there's certain pieces of information we want to know about our nucleus. So what's in the nucleus? We have protons, neutrons, and electrons, right? Because we fall right into the trap of just saying things. Let's slow that down. Where are the electrons? Outside the nucleus. So the only things I care about are the protons and neutrons that need to go in. Because of that, I could immediately cross out the electrons because that's irrelevant to the overall question. I'm really only concerned about the protons and neutrons. Okay? When we're talking about the nucleus, what's the important part of the nucleus that we're actually concerned about? Which comes to now a historical context of why this notation exists. It actually is not the protons. Well, then it must be the neutrons. Not really the neutrons either. Okay? Our concern is the nucleus. Well, why would we be concerned about the nucleus? How many times do you work with uranium? Plutonium?
Never.
Never. Why?
Because they're dangerous.
Why are they dangerous?
Because they're radioactive.
What are they used in?
Bombs.
There you go. And then what kind of bomb are they? Atomic bombs. Hey, we follow the atomic notation there. Okay, or nuclear bombs. Okay, so we're not worrying about those elements because something about those elements does radioactive damage, falls apart. Okay, the nucleus must be falling apart. Well, why does the nucleus fall apart?
Because it's unstable.
Why is it unstable? Because hydrogen's fine, helium is fine. Okay, so there's an interesting dilemma. As we add more protons to move up to different elements, the charge isn't balanced. The protons just start building up. And what happens when I bring two protons near each other? They repel away, but they don't repel away if I can get anything larger than hydrogen. So why do they not repel away? I add neutrons. Neutrons are effectively my glue keeping those together. So if we consider protons as marbles, right? When I put two marbles near each other and I shake, they'll roll away from each other. So what do I got to do? I got to add some glue to make them stick to each other. Okay? And the more marbles, the more glue I have to do until eventually what starts to happen? They already stuck when I put the glue in. But if I keep gluing marbles to this thing, what's eventually going to happen? It's going to be unstable and the whole gooey mass is just going to fall apart. That whole gooey mass fall apart is nuclear decay. Right? That nuclear decay has to do with not just the number of protons or just the number of neutrons. It's the balance of our protons and neutrons, which means the most important thing for me to look at when I'm looking at nuclear notation is not the protons or the neutrons, it's the protons and the neutrons. So if I add my protons plus my neutrons, I would get what is known as my, thank you, mass number. That mass number needs to be the first thing I see when I'm looking at a label. So that mass number will be getting written in the upper right-hand corner. So I'm going to take my protons plus my neutrons, 25 plus 30, assuming I'm doing my math right, 55. Okay. The next thing I might want to know is what element is this? Because if I look at a proton mass of 55, I could jump to, I don't know, iron or manganese and be like, well, those aren't that dangerous. Okay? Those aren't radioactive. Okay? So it's not just the mass, it's what element is holding that mass. So what next thing I want to see is probably actually the symbol for this element. Well, what determines the symbol? The amount of protons. If I've got 25 protons, we're looking at element. Look at that. Manganese, so Mn. Okay. And then let's say that, someone's a sloppy writer and it's really hard to see what they wrote. We might want some redundant information to help make a little bit more clear about what that was. Okay? And because we can't read the symbol, we would need an extra number. That extra number would represent the amount of protons held by that element, and that gets written in the lower left-hand corner. That left-hand corner being here, 25. That is now known as my atomic number. It is redundant because Mn is defined by that. So the symbol tells me that number. Okay? Now I just have to find the element that matches, or the answer that matches that pair up, and we're looking at, looks like C. Why else might we stack the numbers in this way? One thing you might want to do is calculate the number of neutrons. 55 minus 25 is 30. It's almost like it's organized in a fashion that would allow you to determine the number of neutrons straight out of the formula. Make sense? Does that help? Okay. With that, we'll go ahead and stop today. Again, continue to practice. Find questions that are giving you a hard time. Start working on those and hopefully come into class on Wednesday with a list of questions.